Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture number 27 in the course Advanced Robotics. In the last class, we looked at the topic of multi-fingered manipulation, where we saw that when you hold an object, it involves two parts. One is grasping the object, that is, you just hold the object such that it doesn't fall. For example, I'm holding this mobile phone. The second is the manipulation part, where I'm going to manipulate the object and give it some motion. So in the last class, we looked at what we mean by force closures and firm closure. And we also saw that at the fingertip, we have twists and wrenches that can be applied depending on whether it is free motion or it is constrained motion. Now, today we'll see that if we have an object like this and I want to impart some motion. Okay, so I want to impart some motion. That means I want to manipulate the object. Now, how do we manipulate the object? First, you must grasp it. Okay, that means you must have internal forces. Second is, if I want to move it in a particular direction, like this, for example, I want to rotate it, then I have to apply forces using this finger. Okay, or there must be some velocity at this fingertip, and because of these velocities at the three fingertips, there will be a resultant velocity of the object. Okay, so there are velocities at the fingertips which I'm imparting from my motion of the fingers, because of which there is a velocity which is the object is getting at the CG of the object, and the relationship between the fingertip velocities and the object velocity is given by the grip matrix. So today we'll look at the grip matrix. That means how do you impart motion to an object like this. Okay, then we'll move on to an advanced topic of bipedal locomotion. So we'll start off with the concept of locomotion. What is locomotion? Then we'll look at quadrupeds. That means four-legged robots like dogs, okay, or cats. Then we'll come to bipedal locomotion and look at concepts of balance. Then how do you optimize the gait? What is gait? And what is stability of gait and things like that. Okay, so today we are going to very briefly discuss about, or rather we are going to complete what we were doing in the last class. That is, if you're trying to move an object, that is, I want to give some velocity to the object. Let's say this is my center of the CG of the object. I want to give it some velocities, linear velocities and some angular velocities of the object itself. Okay, or I want to impart some forces at the center of the object. Now, how do you do that? You have to apply some forces here or velocities there, because of which the object is going to move in a particular direction. Okay, so what is the relation between the forces acting at the fingertip and the forces that are acting at the center of the object? Similarly, what is the relation between the velocities at the fingertip and the velocity of the object? That is given by our matrix, which is called the grip matrix. So today we'll see how do you determine the grip matrix. And before we go there, I'll very quickly revise what we had discussed in the last class, so that there is some continuity. So in the last class, we saw that when we are analyzing this multi-finger manipulation or grasping, we talk in terms of twists and wrenches. And why is that so? It is essentially because the object can be in free motion. That means when there is no contact like here. In that case, we can apply twists or linear and angular velocities at the fingertip along a particular axis. Okay, so twists when there is no contact. And when there is contact, we can apply wrenches. That means in this case, I can apply forces and moments about the axis at that contact point. So we have twists when there is no contact. We have wrenches when there is contact between the fingertip and the object. Now, what is twist? It's a collection of linear and angular velocities along or about an axis. And how many do we have? We have 6. So Vx, Vy, Vz, omega x, Wx, Wy, and Wz. Now, what are wrenches? Wrenches are the forces and moments acting about an axis at the contact points. So at contact point. Okay. And how many forces can there be? There can be 3 forces: Fx, Fy, and Fz. And how many moments there can be? Mx, My, and Mz. And again, we have 6. So you have 6 here and 6 there. Okay. Now, depending on the type of contact that we have, you can have twists or you can have wrenches. That means when there is no contact, we can have twists, which basically mean that all these motions are possible. Okay, and there is no wrench. So there is no wrench. That means no force and force or moment can be applied because there is no contact. When you have point contact with friction, then we can have twists which are here. Only one twist is constrained, that is the one in the z direction, this direction. Okay, why? Because you can't move in that direction. It is constrained because there is an object there. Okay, so only that the vz you don't have, the other ones you have. Okay, so you have the wx or omega x, omega y, omega z, vx and vy and vz you don't have, and that is equal to 0. Now in place of vz, because there is a constraint there, now I can apply a force in this direction, and that is coming here as fz. Okay, so I can apply a force in this direction, and I cannot apply moments in any other direction or forces in any other direction. Why? Because there is no friction. Like, it's like saying that on this object, if we have this point which is being applied, we apply a force here. Because there is no friction, there is no normal reaction, because mu is equal to 0. So you can apply only one force. You cannot apply any moment because there is no friction again. Okay, and there is no surface contact. So point contact with friction basically means you can apply 5 twists and 1 wrench. Now, this is the analysis that we have to do first when we are looking at how contact is being made between the fingertip and the object. After that, we need to write down our equation, which comes out, which is of the form F is equal to W into C. Okay, that is something we have seen. So for example, let me look at this figure here. It becomes clear that this is an object. So this is my object, and this object is grasped by 2 fingers. One finger is here, which is having point contact with friction, and this is having soft finger contact. Okay, and this is point contact with friction with mu. Okay, now what are we trying to do? We are trying to find condition of static equilibrium, which means sigma f must be equal to 0 and sigma m must be equal to 0. Forces and moments in the x, y and z directions must be equal to 0. Okay, and this is for static equilibrium. So what are we getting is this force is equal to W into C. Okay, and this is what I was talking about. F is equal to W into C here. So this is the external forces, external fingertip forces. Okay, this is my this is the external, not fingertip forces, this is external force. This is my external forces, okay, on the object. C is the fingertip force. Okay, now I want to find what is C. So C is equal to W hash into F plus W hash into W minus I into lambda. And we saw that this solution comes in 2 parts, which C is equal to C into particular solution plus C into homogeneous solution, CH. Okay, and this basically happens. This is not equal to 0, and it happens because W is a pseudo inverse, because it is not an exact inverse. Okay, that means this term will not become equal to 0. This will not be 0, and you can have multiples of that, and this is a positive constant. Okay, so now what we are seeing is that even if the external forces are 0, which means that if the weight of the object is 0, even then you'll need fingertip forces. Okay, and those fingertip forces will belong here, which is in the null space, and this will be forces in the null space, also forces which we call as internal forces. That means for grasping, it is required that you need internal forces, otherwise you cannot grasp. And for manipulation, you need extra forces over and above the internal forces, such that you can give the body a particular velocity or motion in a particular direction. Okay, so this is our fundamental equation that we are writing here. And just to understand better, we are here looking at this example where we have a point contact with friction on one side. Okay, so the finger here is point contact with friction, and the other side is soft finger. Now in soft finger you have 3 forces, 1 moment. Point contact with friction, you have only 3 forces. So when I'm writing this equation, F is equal to W into C, what is the size of this matrix? 1, 2, 3, 4, 5, 6, 7. So it is a 6 into 7 matrix, which is non-square. Okay, so what is the solution of this? The solution of this would consist of the CP, okay, which is the particular solution, and the CH, which is the homogeneous solution, which is equal to 1, 1, 0, 0, 0 into lambda. Okay, so this is my internal forces. Now if you go back, we need to understand this in terms of the physics of the problem, that even if the external forces here are equal to 0, that means, for example, this object doesn't weigh anything, okay, it has no mass. In that case also, you must have W1 and W2. Otherwise, you cannot have this grasp. Okay, so it's like saying for a weightless object also you need force to hold it, which is true. Okay, so what are the internal forces that are required? W1 and W2, which is shown here. So this is my W1 and this is my W2. Others can be 0. Okay, what are the other multiples of this? It is this Cp solution into lambda, and this is a positive constant. Now the internal forces are always positive, and we have to keep them positive such that the grasp can be maintained against arbitrary disturbances. Otherwise the grasp cannot be maintained. Now please note and please understand that we need to find out what are the internal forces. And so if I come back to this equation here, let me go back here. These are the forces that cause motion. Okay, and this is the force that causes grasp. So if you want to grasp the object only, then you need CH. And if you want to have motion also, then you need Cp. Okay, Cp, and the total solution is Cp plus Ch. Okay, in terms of forces. Now this was another example where we are having two soft finger contacts. Soft finger contact would mean that there are 3 forces and 1 moment. So there are 4 on this side and 4 on that side. So there is 4 here. Now there is 4 plus 4, and this is W8. Okay, so this matrix is 6 by 8 matrix. This is also non-square. Now in this particular case, if I want to find what is C is equal to Cp plus Ch. Now only for grasping you need Ch. Now what will be Ch here? What are the internal forces here? Number 1 is I need this force, W1 and W2, which is coming here, W1 and W2. Apart from this, we also need the moments. There is W8 and W7. So this is W7 and W8. So the internal forces are this one plus that one. Okay, so internal force and internal moment. In this case, we have internal force and we have an internal moment. Apart from this, if you want to manipulate the object, now you need to apply more forces. You need to apply Cp also. Okay, so this is for motion or moving the object. This is for equilibrium, static equilibrium. Sorry, this is only for grasping. Okay, now this gives us an idea of how do you decide the internal forces. Now let's see that I want to move the object in a particular direction. Okay, so this is an object, the green color object. This is my object. Okay, now I want to move this object in a particular direction. Okay, that is basically I want to move it in a particular direction such that we can find out the velocities of the object. Okay, in a particular direction. Okay, so what we are saying is that this is an object and I want to move it, let's say, in this direction with some velocity. Okay, now let us say that the forces that are being applied on this object by 3 fingers, these are 3 fingers, let's say, these red ones are fingers and they're making contact here, here and here. Okay, now at the fingertip contact, it is applying force F and velocity is V. Okay, forces are contained in F and the velocities are V. Okay, and in the center of the object, the resultant of all these forces is F and the velocity is gamma. Okay, now basically we want to know what is the relation between this and this now. That means if I want a desired force in the center of the object, what should be the fingertip forces? Or in other words, if I want a desired velocity at the center of the object, then what should be the corresponding velocities of the fingertips? What is the relation there? Okay, so if I want to manipulate the object, I have to give fingertip velocities, right? Now what should be the fingertip velocity to get a particular velocity at the center of the object? That is what we are trying to do. Now this can be used for grasping and manipulation as shown here in the figure. Now in the bottom figure here, what we are seeing is multi-agent systems. So for example, there's an object which is moving like that, and these are agents which are agents or mobile robots which are going and capturing it. The problem is exactly the same. Okay, so first you capture it, grasp it, then here you move it in that direction. How do you move? You place these robots like this and you push. Okay, so because of this motion of this small robots here, mobile robots, this object will have a resultant velocity which is gamma. So we want to find what is the relation between that gamma and v, and that is basically what we mean by the grasp matrix. Now let's say that F, which is the center or the force at the center of the object, is equal to G inverse transpose into F. Okay, and this fellow, let us say this is my relation. So F transpose is equal to F transpose into G inverse. Okay, so I take the transpose of both sides, and from here what I get is F is equal to G transpose into capital F. I get this equation. Okay, so this is one equation that I'm getting. So what I'm saying is I'm finding the relation between this and that. So I'm writing the relation by a matrix G inverse transpose. Okay, and so from this equation I get this equation. Okay, so F is equal to G transpose into F, right? And from this equation I can also get that one. F transpose is equal to F transpose is equal to F transpose into G inverse. Okay, now this is one equation that I have, which is going to give me the relation between the fingertip force and the force in the center of the object. Now what I do is, let me explain what we are doing. We are saying that this is applying a force and it has a particular velocity v. So force is F, velocity is v. So it is imparting energy into the object. Okay, and the sum of that energy of all the energies that are imparted by the object, okay, that will be converted into the energy into the gross motion of the object. Okay, so what we are saying that the power input, okay, v is the velocity at the contact point, F is at the fingertip force, right? Now the power input is v transpose into F. This is v transpose into F, right? This is the power input to the system. Okay, now this is the power input at the fingertip. Now gamma is the object velocity, which is given by this. Now this gamma is made up of small components, which is Vx, Vy, Vz, omega x, omega y, omega z, and gamma 1, gamma 2, gamma 3. These are virtual velocities. Suppose the object is deforming. Okay, in that case these gammas will be there. That means the object is deforming at the center. In that case, the power that is input is equal to F transpose into gamma, which is equal to small fx into Vx plus Fy into Vy. Now we can equate the power input at the fingertip to the power which is getting input into the object, and we are equating both of this, right? So from here, if I take on the other side, on this side, if you remember the earlier equation, F transpose into gamma, which is F transpose into gamma, so F transpose is equal to F transpose into G inverse. So what I do is I put that in here. So this part, this part is equal to this. Where did I get that from? That is from here. Okay, so from here I have got that from this equation. From this equation I'm getting this equation. Okay, so F transpose is equal to F transpose minus 1 into G inverse G. So if I put F transpose there, what I do get is so I'm putting this one here. I'm getting F transpose into G inverse into gamma, and Ft and Ft cancels here. So we are left only with V and we are left with gamma. What is gamma? Gamma is the velocity of the center of the object. What is V? V is the velocity of the fingertip. Okay, so if I take the inverse of this, or if I bring G onto this side now, then what will happen is gamma will be equal to G into V. So gamma is equal to G into V. Okay, so that is basically G is basically called the grip transform matrix. Okay, so this is giving me, the G matrix is giving me the relationship between the velocity at the fingertips to that of the velocity at the center of the object, and it is related by the matrix G. Okay. What does this matrix G consist of? Now if you just look at the earlier case where we had looked at, so it will basically consist of this matrix plus the internal forces. Okay, so if you remember what we had done, some time back. Let me go back and try and explain this matrix, the G matrix. I'll just write it here. So grip matrix, what does it mean? Suppose I have my forces like this. I have a two-finger grasp, okay, and this is my working at the center, fx, fy, mz. This is fx1, fy1, fx2, fy2. In that case, what we see is that when I write my equation, f is equal to c omega into c, then this is equal to 1, 0, 1, 0, 0, minus 1. Okay. Now, the matrix G will consist of this. G is a square matrix. So it basically will need 4 inputs, right? So it's fx1, fy1, fx2, fy2. So there are 4 of them. So this has to be a 4 by 4 matrix. So I need to add one more column. Now, which is going to be that row that I'm going to add? It will be the internal forces. What are the internal forces? fx1 and fx2. So it is 1, 1, 0, 0. That is my, sorry, that is my internal forces. So now it becomes a square matrix. Okay. Now this becomes a square matrix. So basically what I'm going to get is I'm going to get the relationship between the object velocity at the center and the fingertip velocity. G is a square matrix now. So what happened is we looked at the matrix W plus I added the internal forces there and it became a square matrix. Okay. So please think about this. How do you get the relationship between the object velocity at the center and the fingertip velocities? Okay. Now let's proceed from here to look at the next topic, which is biped locomotion. Okay. Now locomotion basically means going from one place to another place. As shown in this figure here, this cartoon figure is walking, swinging its hands very happily and walking, and it's going from one place to another place. So locomotion basically means moving from one place to another place. Okay. Now there can be different ways by which you can move. For example, you can walk, as is shown in this figure here, cartoon figure. Then you can run. Okay. You can swim. You can fly. So all of them comes under the same category of you're moving from one point to another point. Okay. That is what it means. Moving from one place to another place by walking, running, swimming, flying, rolling, etc. Okay. So here we'll be first looking at introduction to legged locomotion. We can talk about passive and dynamic systems. Then we'll talk about optimal design and gait, and then we'll look at a little bit of motion planning in 3D. So these are all examples of locomotion. There's a dog which has 4 legs and it walks on 4 legs, okay, or runs on 4 legs. This is a fish which is swimming. It's also locomoting. It is moving from one point to another. This is a bird which is also moving from one point to another point by means of locomotion. Okay. Now, before we proceed, we should understand a few points here. First of all, why do we need to study biped locomotion? Of course, we want to do research and build robots that can behave like humans. That's great. But then why are we studying biped locomotion? First of all, understanding biped locomotion gives us an understanding of the biomechanics of how we walk, design active prosthetic systems, okay, like artificial limbs, effect of disease like osteoporosis. Okay. So if you understand the biomechanics of walk, we can understand concepts of design, or we can design better systems in terms of prosthesis or in terms of understanding progression of disease, etc. That is one. The second is robots living in society need to have human-like features, hands, legs, face. Okay. So robots living in society normally move around because they have hands, legs, and face. They also walk around and behave like humans. Walk around and behave like humans. Okay. Now all man-made structures are designed for human locomotion and use, and hence robots which have legs also should be able to walk around, because all man-made structures are designed for human locomotion. Now there is a lot of requirement and a lot of application in entertainment, movies, pets. There are a lot of science fiction movies like Star Wars, and where they use robots which can walk around. Pets, robot human cooperation, rehabilitation, understanding prosthetic limbs, etc. Okay, so this is why studying biped locomotion would give us a deeper understanding to concepts like first of all is locomotion, number two is biomechanics, number three is it will enable us to design better systems. Okay, now very interestingly, biology prefers legs over wheels. You will not find any biological entity which has wheels. Okay, so wheels do not exist in is not a biological entity. Okay, fishes use fins for swimming, birds use their wings for flying. Okay, but you never find a wheel, a biological entity having wheels. Okay, we have human beings use cars and bicycles which uses wheels, but biology doesn't prefer wheels, it prefers legs. Now all biological entities either have legs, wings, tails for locomotion. Okay, and one of the disadvantages of legs is that legs require more energy but are multifunctional. So legs require more energy for motion but are multifunctional. What is this multifunctional? For example, you can sit down, you can run, you can walk, you can lie down, etc. Okay, now very recently the earliest robots were wheel robots. Okay, so this is a wheel robot. Okay, so the earliest robots were all wheel robots. Why were they wheel robots? Now essentially because wheel robots are balanced. They do not need to be balanced. Okay, if you have a tricycle or you have a four-wheeled car, the car is balanced. You don't need to balance it. It doesn't fall down. Like a bicycle, you need to balance it. But a four-wheeled car, you don't need to balance it. It stands by itself. That is the reason why the early robots were all wheeled. Okay. Now there has been a recent interest in legged locomotion because legs have some advantages. For example, these are some advantages of legs. They can walk over obstacles. For example, if you have a flat terrain like this and you have obstacles like this. Okay. Now a wheeled robot which has four wheels, okay, will not be able to go over this. It'll either have to avoid but can't go over. But if you can think about a legged system, this is a legged robot which is standing there and this has legs. It can simply take its legs on top like this and go on the other side. Okay, so it can walk over obstacles which wheel mobile robots cannot do. It can climb stairs. Okay, it can go over obstacles. It can run over on top of ditch. So for example, another example I give is there is a ditch here. Okay, so there's a wheel mobile robot which is here, which has wheels. And obviously it can't go, it will fall inside the ditch. But if you have a bipedal robot like this, it can probably take a step and go across the ditch, which a wheel system cannot do. Okay, so this is the advantage of legs over wheels. Disadvantage being that you need to balance it and it consumes more energy. Now foot normally has less footprint. Okay, now what do you mean by footprint? So if I look at a vehicle going, this is my vehicle top view. These are four wheels. When the vehicle is going, it will have tracks. Okay, whereas if you have a biped robot, it will just have lesser footprint. It is just putting its foot. So there is less footprint as compared to a mobile robot. Now the other advantage is the body can be maintained at the same height. Okay, this is something very interesting. I don't know whether you have ever observed that when you walk, your eyes are maintained horizontal. So this is your eyes. Okay, so these eyes are maintained always at the same level, which means that the horizontal is kept horizontal always. Okay, this is always required for us to keep the eyes horizontal. Why? Because this is used as a reference. Okay, so now suppose you find that your reference is bent or crooked, then it's a question whether the reference was crooked or you were crooked. Okay, I hope you understand what I'm saying. So this basically requirement is there that the body can be maintained at the same height, basically for vision, having the vision field as horizontal. Okay, this is useful. Now legs can perform different functions like climbing stairs, sitting down, etc., which wheels cannot do. And that is the reason why biology prefers legs over wheels. Okay, because of all these advantages. Now, just for interest, that when Karl Kapek first used the word robotics, we said that the word robot actually came from the writings or the drama of the Czechoslovakian writer Karl Kapek, whose play depicted human-like mechanical men, and he said that in future there'll be mechanical men who will do dirty work in industries. And this is apparently a picture of a photograph in which, if you look at, here is the mechanical man. Now the mechanical man is actually a biped, it has 2 legs. So the origin of the word robot actually is for systems which have 2 legs. Although the advent of or research into 2 legs started off much later, essentially because this concept of balance, energy came much later, after we understood a lot of robotics in terms of dynamics, kinematics, control. Okay. Now, 1942, Isaac Asimov first used the word robotics, and in most of his fiction, he would be depicting humanoid robots. Okay, humanoid robots have legs and they have arms. Okay, so in most of his writings, he would be depicting robots as humanoids which have legs and arms. So this is just for interest, historical interest, that the word robot actually came from this drama or play in which it was a robot which had legs, actually 2 legs. It was a biped. And Isaac Asimov also talks about robots and robotics, where most of his robots are humanoids which have legs. Okay, so the early study and the very concept of robots and robotics are for systems which have legs. Okay, now function of legs. So we have I can draw that this is the body. Okay, now this is the body. So what is the function of legs? So the first function of leg is to carry the weight, or rather to support the weight of the body. Support body weight. Okay, so that is the first function of the legs, support the body weight. Now, how many legs? They are normally even numbers. Okay, so it is 2, 4, 6, 8. You don't normally have odd numbers. You don't have 1, 3, 5. This you don't have. Okay, why? Because of symmetry. Mainly because of symmetry. So if I have 4 legs, I have 1 here, 1 there, 1 here, and 1 there. Okay, so these are the 4 legs that I have for this. Or I can have also 2 legs which are standing like this and like this. Okay. So you have even number of legs, 2, 4, 6, 8, because of symmetry, so that there is symmetry here and the load is equally distributed between this leg and this leg. So that is the first function of legs, is to support the body weight. Okay, and how many legs? Basically it's an even number, 2, 4, 6, 8, like that. Next is to move the body forward. That is what we call by locomotion. Okay, so if I have my side view here, let's look at this figure. How it is going to move forward? It is going to move forward by taking one of the legs up and putting it forward like that. Okay, then the body moves forward, then the other leg also moves forward. Okay, so you can imagine that this is my 2 leg. Let's talk about 2-legged system. So there's 2 legs like this and like this. Okay, how is it going to move forward? So first the rear leg, this is my rear leg. The rear leg will move forward like that, and the body will also move forward. Okay, so the rear leg will move forward like this. This is my rear leg. It has come like this now. Okay, and the body has moved forward. So this leg is still here like that. Okay, if you can imagine what I'm saying. Now the rear legs, now this figure is not very correct, so let me draw it again. This is one leg, that's the hip joint, this is another leg. Okay, so this is a 2-legged system. How does it move forward? The leg goes like this, so the body also goes forward. It comes here and here. Okay, so this leg has come there now, and this leg is still here. Okay, so that's how the body has gone forward. And that basically means that you move one of the legs forward or 2 of the legs forward, and and then as a consequence of which the body goes forward by some distance. And this is how the body moves forward. So the function of legs is to support the body weight. How many legs? 2, 4, 6, 8. Okay, because of symmetry. And then the whole objective is move body forward. Okay, that is how it does move the body forward. Now, the interesting thing is, the first thing that we need to do in design of a legged system is we need to decide the number of legs. Okay, you can have 2 legs, 4 legs, 6 legs, 2, 4, 6, okay, 8, but not normally odd number of legs. Now, once you have decided the number of legs, then the next question is, how do you place the legs? Okay, we have studied kinematics, so we see that for a 2 degree of freedom system also, there are 2 solutions, right? Sometimes there can be more than 2 solutions. So depending on where you place your legs, for example, this is the frontal direction. The legs are placed like this. This 1 degree of freedom, this is another degree of freedom, if you can imagine. This is 1 degree of freedom, this is another degree of freedom. Okay, so in this particular case, the body is moving in the frontal direction. In this case, the body is moving in the sagittal direction, the side direction, just like a crab. Okay, this is something like a dog, although dog legs are not like this. Okay, this is a mammal. So a mammal is a dog, for example. The legs are straight down like this. Okay. In the case of a reptile, say a lizard, the legs are like this. Okay. So all of this have 4 legs, but the design is different. So what I'm trying to explain is that the first thing you need to decide is how many legs you need. So it can be 2, 4, 6, 8. And after you've decided the number of legs, then the next question is, how do you fix the legs? From the side, just at the bottom, and from which side? That determines the direction in which the system is going to move forward. Okay. Now, what about the shape of legs? Here only we talked about the number of legs and where it is going to be fixed. What about the shape of the legs? For example, in a biped also, legs can be straight down like this. Okay. In the case of reptile, it is like this. In the case of cockroach or other insects, it is like this. Okay. So this all have 2 degrees of freedom each. They all have 2 DOF or 3 DOF, but the shapes are different. Now, in the case of a human, we spend a lot of time standing. So if you think a little bit, this is my MG, which is acting downward. If it is straight down like that, what is happening is this leg is having a reaction here and a reaction there, which is mg by 2 and mg by 2. So it is symmetric, and the body weight is being supported straight through the leg. Okay, that means if this is my body, this is the leg, the force is going there and going straight through like this there. Okay, whereas on the side, now here if you see, the force is here, the reaction force, and there is a force into a distance, so that's force into x. So there's a moment which is coming now. In this case, there is no moment. Okay, so in this case, if you see, this is my leg, so basically it is here, the force is going straight through that joint, so there is no moment. Moment is 0, only force is there. Whereas in this case, there is a moment, force into x distance, that's my moment. Okay. Which means that this torque has to, this leg must provide a resisting torque such that the body is kept at that position. So it means that it needs more energy. Okay, this needs more energy, this needs less energy. Why? Because it doesn't need a moment. This one needs a moment. What about here? Now here the moment arm is this complete distance here. Okay, that is the force into that distance, and this is the length of the legs. So the moment arm is force into y, this is the y distance, and because the legs are long like this, it can jump, okay, much higher. So this is basically legs of insects. Okay, now insects sometimes, like cockroaches, they need to jump and escape. Okay, that is why their legs are shaped like this. Now the other reason here for this design is that this is for reptiles. Okay, reptiles means lizards, house lizards. So this lizard will be climbing walls. So it climbs walls, right? So if it is climbing the wall, then this force into the distance, so this is the mg into the x, that is the total torque that has to be resisted at that point. Otherwise it will fall when it is climbing on the wall. So which means that the body should be near the ground. Okay, the more near it is to the surface, the lesser torque you need to support. So the reason why the legs of a reptile or a lizard is like this is twofold. Number one, it is it needs to climb, and if it has to climb surfaces, vertical surfaces, it needs lesser torque to be it needs to maintain the body close to the surface, so that the torque requirement at that contact point between the leg and the surface is less. Okay, in case of insects, they need to jump and escape, so that is the reason why the legs, the moment arm is large, so they can produce very high torque and suddenly move and change directions. What about mammals? The reason is the same. The force goes straight through here and it goes through here, so which means that this is the force here and the force here, and there is no moment at this point. Okay, so there is no moment being supported here, hence energy requirement is less. Okay, so reptile, there is an energy requirement there, but then the body can come close to the ground, so the torque requirement here is less. Okay, these are legs designs again which are not used that much. Okay, so now I hope you understand why in the case of a mammal the legs are straight down like this. Our legs are like this because the force goes straight through and there is no moment requirement there. Whereas in the case of a reptile, it has to be close to the wall such that the moment requirement is reduced. Okay, now relative length of legs. Insects like the spider, okay, which has 8 legs. Now there is a relative length of the legs. Now some of the legs are long and some of the legs are short. Say for example, this is short and this is long. That is essentially for a particular gait. Okay, now the relative length of the legs determine the gait. That is something which we'll see. Now, very interesting to note, tail can also be used for balancing. Some insects have tails. For example, you can look at this figure here. So when it is climbing up, what is happening? This is my CG. So the CG has to be on the support. Okay, so what it can do is it can swing its tail up, so that what is happening is that the CG is moving forward. Okay, in this particular case, if you see, it is standing such that the effect of the tail is to bring the CG inside the foot support polygon. Tails can also be used for getting up. This is an insect which doesn't have hands. Interesting case. So if the insect falls down, it can use its tail and get up. Okay, so the tail is basically used for balancing. Okay, and for dogs and all, when they run, they make use of their tail for balancing also, because it can shift the position of the CG. This is one of the best examples of a quadruped robot. So this is a quadruped, which means 4 legs. It has basically 1, 2, 3, and 4 legs it has. And this quadruped robot was designed by Boston Dynamics. Look at the shape of the legs. Okay, the legs are bent inwards. Okay, so the leg is like this. Okay, just have a look at the shape of the legs. Okay, now the other thing that you look at is, number 1 is shape of legs, whether it is bent like this or it is bent like this. Number 2 is look at legs in air and ground. Okay, so there are 4 legs. These are the 4 leg contacts. Please watch them carefully. How many legs are being lifted at one time and the body is going forward? Okay, look at the shape of the legs and look at the let's have a look at this video, and please note very carefully the shape of the legs. Please note that the shape of the legs is bent backwards, and also look at when the legs are making contact with the ground and when the legs are on top. Okay, now what you'll see here very carefully is that if I draw the top view of this, there are 4 legs like this. The legs are moving in diagonal fashion, which means that these 2 legs are in air while the other diagonal legs are on the ground, and then it switches. The other legs are on the air and then this legs are on the ground. Okay, so basically it switches like this and like that. Okay, and that pattern of foot placement is what we call by gait. So please look at this video very carefully. This is Big Dog, built by Boston Dynamics, and it is probably one of the best quadruped robots in the world. And it has a gait such that at any instant it is lifting 2 legs on the air, and the other diagonal legs are on the ground. Okay, look at the shape of the legs. They are bent backwards. Okay, unlike in the case of a dog where the legs are bent in the forward direction. Okay, so note very carefully how the contact is being made and how diagonally the legs are going up and coming down. This is basically what we mean by a gait. So gait is the pattern of foot placement, how the foot is being placed and how the body is going forward. This is showing the stability of the system, that when it is subjected to an external disturbance, it can very easily change the position of its legs, and it can absorb the shock. Okay, it doesn't fall down. Now this is very difficult even for a dog, or you might say if a human is pushed, a human can fall very easily. Now this is a more advanced robot, which is Atlas. So Atlas is also developed by Boston Dynamics. Please note the shape of the legs. So if I see, this is my side view, there is the shape of the legs which are bent like this. Please note that if this is my hands, the hands are not moving much, but the legs are bent like this. Okay. Now there are two legs. So if I take my front view, there will be two legs, one leg here, one leg here. So at any instant, one leg is on the ground and one leg is in air. Then both legs come on the ground and then the other leg goes in air. So look at this video very carefully. This is Atlas, and it can walk on very difficult terrain like snow, and in kind of terrain where even human beings would find it very, very difficult to walk. Please note that the legs are bent. The robot walks with a bent knee, and that is basically for stability. When we come to stability, I'll explain why it does that. Okay, so look at the shape of the legs and look at how the foot placement is being made. So it is on one leg stance, two leg stance, then one leg stance. And that is exactly what we mean by pattern of foot placement. So if you look at any leg, the leg has two conditions. It can be on ground or it can be in air. Okay, so it can be on ground or it can be on air, right? So if it is on ground, we mark it with a black spot, and if it's on air, we just leave it blank. Okay, so in the case of the humanoid robot or a human being, we can say that we have two legs, one leg here, one leg here. Okay, so either both the legs are on the ground or one leg is in air and the other one is in ground. So this is my right leg, that's my left leg. Okay, so if I draw my gait diagram, this is my right leg, this is my left leg, and at different instants of time, this is T1, this is T2, this is T3, and this is T4. Okay, so initially when you start, both the legs are on the ground, so I'll mark it as black. Okay, so both legs are on the ground. This is what it means. Next, what you're going to do, one leg will be on the ground and the other leg is going to go in air and the body will move forward. Then the next instant, that is T3, so that's T3, that's T2. What is going to happen? Both the legs are going to come on the ground. Okay, and then one leg is going to go in air. So this is here. So this leg was on the ground. Now the reverse, this will be on the ground and the other leg is going in air. Okay, then what will be the next one? Well, you can guess, it is going to be both on the ground. What will be the next one? So if this one is on the ground, then that will be on the ground. Okay, so now this is the pattern of foot placement, and this is what we call by gait. Okay, in the case of a quadruped robot like this, something similar to what we saw for the big dog, when there is a black mark, it basically indicates that's the leg on the ground. So there are four legs here. Okay, so if this is my front direction, this is the right front, this is the right back, this is the left front, and that is the left back leg. So there are four legs here, you can see. The right front, right back, left front, left back. These are instants of time, T1, T2, T3, T4. Now, it has started off by two legs in air, this and this are in air. So only the right front and the left back are on the ground. Okay, so it is marked by black, this and this. These are in air, so they are not marked, indicating they are in air. Next, from here, this is the next instant of time, all four are on the ground, so it is all black here. Then what happens, the diagonal, so this was like this, the next one becomes like this. Okay, these two are in air. Then all are four are on the ground, then again two are in air, and then they are on ground. So it is ground, air, ground, air, like that. Okay, now obviously there are four legs here, right? So because there are four legs, you can either take two of them in air or you can take only one of them in air. I could have kept all three of them on the ground and only this leg goes forward. Okay, that gait is also possible. Okay, in the case of a human, that is not possible. Why? Because you have only two legs, you don't have a choice. So either one leg is on the ground or both legs are on the ground. Whereas in the case of this robot, because there are four legs, you can have three legs on ground and one leg in air. Okay, and that is another different gait again. So in that gait diagram, what is going to happen? So left back, left front, right front and right back. It can be three legs are on the ground, one leg is in air. Then all four are on the ground, one leg is in air again. Okay, So you can have different kind of gates for a 4-legged system. For a 6-legged system, there is even higher variety where you can get a different kind of gate. Now, what do you mean by balance? We are seeing that by balance, it essentially means it should not fall down. Okay, the system should not fall down. Now, in terms of static balance and dynamic balance, in case of static balance, we say that when 3 legs are in air, like here, this is a hexaped, there are 6 legs, 3 legs are in air, okay, and 3 legs are on the ground. Now, the legs that are on the ground, if I draw a polygon connecting the legs which are on the ground, then I get this, what we call a support polygon. Now, the projection of the center of mass has to be inside the support polygon. Only then, under that condition, that this system is balanced. So there are 2 margins of stability we talk about here. One is if this is your center of mass projection, then the distance of the center of mass from either of the edges of the polygon, that's D1, D2, D3, we take the minimum of that. And for example, if your center of mass comes here, this will become minimum. This means that you're coming towards a position where the center of mass can suddenly go out and it can fall. So this is something like a stability margin. How stable is it? So when it is exactly at the center of this support polygon, that is the case where you're maximum stable, right? As you're coming nearer and nearer to this edge, you're slowly becoming unstable. When you're coming to that condition, when you're coming to right boundary, exactly at the boundary, then you can become unstable, right? So this is one definition, stability margin. The other one is longitudinal stability. If this is the motion of the body, for example, this is moving in this direction. In that case, this is your projection of center of mass. How far is it from this boundary and this boundary? So D1 and D2. So S1 is the minimum of D1 and D2. This is another margin of stability which talks about the longitudinal stability margin. So as this is moving like this, again the same argument, as it is coming nearer and nearer to this boundary, it is becoming slowly tending to become unstable. And it becomes limiting cases on that boundary, and then it becomes unstable if it goes out. Okay, so this is basically how we define the stability margin, and this is what we mean by gate. Now, as I discussed in the last slide, if we have 4 legs, there are different ways by which you can walk, which basically means you can have 3 legs on the ground, only 1 leg goes up and the body goes up. Okay, now if you have 6 legs, you have even more. You can have 3 legs on the ground, or you can have 4 legs on the ground, 2 legs going up. Okay, you can have 5 legs on the ground, only 1 leg going up. So there are all variations which are possible if you have 4 legs, 6 legs, 8 legs. And this pattern of foot placement is basically called gait. Now, how fast it can walk, how stable is it, would depend on which gait it is taking. Okay. Now, so this is for walking. And we also discussed about the stability margin in terms of static stability. Now, today we'll stop here. Okay, so today we looked at the very basic concept of gate, how stable it is, and how close this projection of center of mass is from any boundary. And we'll stop here today and continue in the next class. Thank you.